So good morning, everyone. Before we get started, I'd like to acknowledge my co-author, Dr. Reddy Carey, who some of you people here were at the PSRI annual meeting, and Reddy was very prominent. He's the president of PSRI and CEO as well. So Peter said yesterday that one of the things he wanted everyone to do when he came to this conference was learn. That was one of the first things. So my first few slides are basically going to be teaching slides. So I hope you will bear with me for the first 3 or 4 slides. And what I'm going to do is try to teach you how to understand the scientific research literature. So we can get started here. So it's going to be set up in a format of what is said and then what is really meant in the scientific research literature. So if it is said that it is suggested that, or it is believed that, or it may be that, it really means I think. And it says it is generally believed that means a couple other people think so too. If it says 3 of the experiments were chosen for detailed study means the results of the others really didn't make sense. And then if it's said that it's clear that much more work will be required before a complete understanding means I don't understand it. And it says, unfortunately, a quantitative theory to account for these results hasn't been formulated means I can't think of one and others haven't either. Okay. So if it is said that typical results are shown means that the best results are shown. And it says if the agreement with predicted curve is excellent actually means fair, good means poor, satisfactory means imaginary. Okay. And if it is said that thanks are due to Scott for assistance with the test and to Smith for valuable discussion means that Scott did the work and Smith explained what it meant. Okay. So that's my job of teaching everyone. So okay. So when Peter called me up and asked me to do this, I said, well, Peter, I'm not a modeler. He said, well, that's fine. He said, why don't you just give an overview of fluidization? So definitely you're not going to get much modeling from this presentation, so I hope you bear with me. Okay. So actually fluidization is 100 years old this year. The Winkler coal gasifier was the first commercial fluidization process, and it was commercialized in Germany in 1926. It was developed by Dr. Fritz Winkler, who worked for the BASF Corporation in Germany, and it was a gasification process. A photograph of the unit I'll show you on the next slide, and then a diagram of the process I'll show on the slide after that. Now, the solids used in the process were large, with an average size of approximately 3 millimeters. And as we're going to see, even in the US and in Europe, what happened is people were using very large particles, group B and D, when they first looked at fluidized beds. And it wasn't until we got to small particles before people really started to develop the FCC process. So here's a picture of the Winkler gasifier. You see it was a going concern. It was a big unit here. And this is basically the gas generator, a diagram of what it has. You brought into the coal here. They really didn't have a proper distributor. It was more like a grate that they had here. They would bring in the oxygen and air and oxygen steam here and actually put it in here again as well. So it was a very simple device, but it was the first commercial fluidized bed. So as I said before, fluidization was being explored in both the US and Europe in the 1920s using the Geldart group B and D particles. And I'll talk about Geldart groups B and D in a little, and most of you people know about that. And so research was conducted in the US, basically by the US Bureau of Mines in the 20s, right? And also in Europe in the 1920s, especially with the BASF, headed by Dr. Fritz Winkler. So from about 1936 until about there, the research was still on large particles, greater than 500 microns in Europe. Fluidization in the US at this time began focusing on smaller particles, less than 100 microns, basically because of the development of the FCC process. And basically it was sort of an accident, as we're going to see, why we went into the smaller particles. So the history of the development of fluidization basically parallels the development of the FCC process. So it is the reason why we have this large fluidization community today. It's sort of the grandfather of all fluidization processes. So this process was important. Whoops, I'm sorry. Let me go back here. I hope I go back. Okay, this process was important in producing high-octane aviation gasoline and butadiene rubber in World War II. And so the government was plowing all sorts of money into development of these processes and that sort of thing. And so it developed very quickly. It couldn't be done, in the same time frame today. But anyway, that's what they did. So there was really a lot of money given to these companies and a lot of pressure put on to develop this process. So the French inventor Eugene Houdry invented modern catalytic cracking, and here's a picture of him, when he discovered that burning coke off a silica alumina catalyst would restore its activity. And he discovered that in 1928. So basically, he's the one who developed catalytic cracking. So Houdry was a French engineer and playboy. Basically, I think in French they call him raconteur, something like that. And so he was really interested in improving the quality of gasoline to improve motor operation. So what he had was a Bugatti car, and he would test his new gasoline products in this car on a calibrated hill. The best gasoline products would get the car further up the hill and that sort of thing. So anyway, he was an interesting guy. So this is a picture of Houdry, and this is a picture of this car that he used, to calibrate and test out the different types of grades of gasoline that he would produce. So Houdry developed this process, and he developed he had patents, and so people were using this process to develop, to produce gasoline. And Houdry's patents were adopted by Sun Oil Company and Saucony Vacuum, which later became Mobil, to produce the first commercial catalytic cracking unit, and it was a packed bed in 1936, and it had big particles. They were roughly about 3,000 microns or so. They weren't the 70 micron particles that you have today. So after a while, other oil companies had to pay a license fee to Houdry, and some of them felt that Houdry's licensing fees were excessive, and so Standard Oil of New Jersey, who was called Jersey at that time, which is now Exxon, was a leader in forming an 8-company Catalyst Research Association to develop a catalytic cracking process outside of Houdry's patents. Okay? So up to this point, work on the FCC process utilized Geldart groups B and D particles with fixed beds and moving packed beds. And so this is basically Houdry's process. He had 3 fixed beds here, and he had different things going on in each particular bed. In this particular one, he had hot air to regenerate the catalyst after steam stripping right here, and that sort of thing. So he had different parts of these, and so we would have these fixed beds, and they would move basically the gases around in that particular type of approach. And so this is a picture of these 3 beds of the Houdry process, basically in about 1936, 1937 or so. Okay, but in 1934, before the formation of the Catalyst Research Association, it was discovered accidentally at Imperial Oil that a small Geldart Group A powdered catalyst could rapidly and catalytically crack oil. And so after some time, the CRA used this discovery to develop their cracking process using fine particles. So that's really why we started to use fine particles with FCC. At this time, the U.S. then began diverging from using large particles. However, large particle work on fluidization persisted in Europe for several more years. So early FCC units using fine particles employed horizontal tubes or coils. It wasn't a vertical fluidized bed like we have today. And so they were having a lot of trouble with these horizontal tubes and coils because of plugging of the reactor. So Professor Warren Lewis and his colleague Gilliland from MIT, they're very famous if you go back into the field of fluidization, were consultants for Jersey. And they attended a meeting when they were talking about the plugging of the pipes and the coils they had. And they proposed operating in a vertical tube and were given permission and funding by Jersey to test this concept at MIT. So the tests at MIT were very successful, and eventually this vertical fluidization concept was adopted by Jersey and the CRA. So interestingly, Lewis and Gilliland said that they were not aware of the vertical fluidized bed used by Winkler in Germany. And they may not have been, but Jersey certainly was. Jersey said that they were aware of this Winkler work, but claimed that it didn't influence the development of their process because the Winkler was a large particle process. Okay. So the first modern FCC process began operating in Baton Rouge, Louisiana, in May 25th, 1942, with the Jersey Exxon we call the Model 1 unit. The original name of the process was Powdered Experimental Catalyst Louisiana, shortened to PECLA, And the Jersey Exxon Model 2 was started in 1944. So both refineries have been designated as National Historic Chemical Landmarks, and you can actually go see them in Baton Rouge. And here's a rather, not a really good picture, but the Exxon Baton Rouge Model 1 is here, and the Model 2 FCCs are here on the right. So you can actually go and see these units. So because of these developments, then, FCC has been called the grandfather of fluidization field, and it's rightly so, because almost all the work that was done early on in fluidization was done in association with the FCC. It got this name, it's got its impetus from World War II, as I said before, to develop high-octane aviation gasoline and butylenes to develop Buta-S rubber and high-octane gasoline. So the development of the FCC process was really a very large factor in influencing the outcome of the war. So after the war, the FCC area grew in parallel with the development of the automobile, trucking, commercial aviation industries, all which used its petroleum products. So even today, the FCC process is still the most important commercial application of fluidized beds. So after World War II, then, developments in fluidization proceeded very rapidly. Fluidized beds were used in the production of phthalic anhydride, acrylonitrile, the Fischer-Tropsch process, and they're also extended to drying of materials. This happened in the 40s, late 40s and early 50s. And then the fluidized bed bubbling combustion processes were developed in the 60s. And then people said, well, we've got this fluidization concept. It has bubbles in it. Maybe we should study bubbles. And so they started to research into bubbles and how it affected these fluidized beds. So from this and earlier work, the two-phase theory of fluidization was developed. And this theory states that all gas in excess of the minimum fluidization velocity passes through the bed in the form of bubbles. So if you have a high velocity in your bed, almost all the gas is going through the bed in the form of bubbles. So the 70s saw the development of circulating fluidized beds, which is basically an FCC riser is a circulating fluidized bed. Circulating fluidized bed combustors are the main proponents of this technology. And the famous Geldart powder classification diagram was developed in 1973. And it's now used by all workers in the fluidization field, which shows how particle size affects the operation of fluidized beds. And I'll show you on the next slide. It's the most famous paper in fluidization. And it was little known, however, when Derek Geldart submitted his paper, to be published. It was rejected the first time. And I was a good friend of Derek, and he was a little miffed about this. He said that it probably didn't have enough partial differential equations in the paper because it was a very simple paper. But, it basically revolutionized how people look at particles in the fluidization field. And so the Geldart diagram looks something like this. On this x-axis, you have particle density minus gas density, and in kilograms per cubic meters, because Derek was in the UK. And here we have particle size in microns right here. I'd like to say one thing here. This applies in ambient conditions. And if you look at the particle density of things like FCC, coal, that sort of thing, the particle density is somewhere close to about 1,500 kilograms per cubic meter. At ambient conditions, say in air, the gas density is only 1. So 1,500 minus 1 is still 1,500. So basically, this is particle density versus particle size. So Derek said that there were 4 different types of groups: Group C, Group A, Group B, and Group D. And Group C material, which is, for all practical purposes, less than about 30 microns average particle size, are very cohesive. It's like flour. You try to get clumps together very quickly. And Group A material, the quintessential Group A material is FCC catalyst, right? You still have some interparticle cohesivity that you have to worry about, but it's free-flowing. And then beach sand is like a Group B material, and then maybe 2,000 micron polyethylene beads would be Group D material. So you get larger particle size as you go here. Now, these categories, when you go between Group A and Group B, it shows a line here. Well, it's a gradual type of thing. It's not going from falling off a cliff when you go from Group A to Group B, and also from Group B to Group D. There is another particular area here between Groups A and C. Some people call it Group AC. It's very nice material to fluidize. It's about 40 or 50 microns and that sort of thing, so very few bubbles and that sort of thing. But if you fluidize in that area, it's wonderful. And also it flows very well in standpipes and that sort of thing. Okay, now this only applies at ambient conditions. What happens is, if you have something that's close to a group B material, or close to this boundary here, and it's a group B material, and you go to high temperature or high pressure, you can cause that material then to behave like a group A. So what's the difference between a group A, say, and a group B material? These two categories right here are probably 95 or 90% at least of all the fluidized beds in existence. There are more group A beds than group B. So what distinguishes between A and B? What's the difference? If you take sand, 500 micron sand, and you fluidize it and shut off the gas, it will thump, it will defluidize very quickly. If you do that with group A material, it will take several seconds. It may maybe take 5 seconds to 15 seconds, depending on the fines content. And so that's a difference. Also, in between, when you get to minimum fluidization point here for group A, bubbles don't form. They will here. They'll form immediately. But here, you have to go to another velocity called the minimum bubbling velocity before bubbles start to form. So there's a region between UMF and UMB where you have no bubbles, but you're fluidized, and that occurs only with group A materials. Okay, now, you guys are probably all too young to remember this, but the embargo of the Organization of Petroleum Exporting Companies, OPEC, against the U.S. in 1973 led to shortages of natural gas and petroleum. And so people who lived at this time will remember the rationing of gasoline and long lines of people waiting to fill their automobiles. For instance, you would go, and if you had your license plate that was ending in an even number, you could get something on a Monday, right? And Tuesday, you have an odd number on your license plate, you could go get gasoline then. So that's how they did this sort of thing. So because of these shortages then, the U.S. government said, what I want to do is not be caught like this again. I want to be able to produce more energy. So they increased funding for several coal gasification plants to produce syngas to mitigate these future oil shocks. So the coal gasification processes were operating at very high pressure, say 1,000 psi-G or 70 bar, and high temperature, 1800 F or 1,000 degrees C. And they didn't have much information on fluidization in this area, so the lack of information in high pressure and temperature saw significant research in these areas during this time. So nearly all of these processes utilized Geldart Group B solids as well. And that's where I got my first baptism into fluidized beds, was because of this particular area right here in the 70s when IGT, that I worked for at the time, was developing coal gasifiers. So the 80s saw the development of circulating fluidized beds and the development of polyethylene and polypropylene fluidization processes. In the 90s and the 2000s, and still to this day, there became an intense focus on process scale-up, system analysis, and the development of simulation tools, such as CPFD software is having today. This time also saw the early application of computational fluid dynamics and their models to fluidized beds and the start of research into very fine cohesive particle fluidization. So this stuff is very hard to fluidize, cohesive particles, because of interparticle forces like flour. But it has such a high surface area to unit volume, people would really like to use this into a fluidized bed if they could, because it's going to be so reactive. So the improvement and focus on modeling fluidization and the work on fine cohesive particles are areas that will be important still in the future, and I'll talk a little bit more about that. So the other major change over this time was the rapid rise of China in the fluidization field. So this can be seen by looking at the number of papers produced by countries over the period from, say, 1980 to 2001. And I'll show that in the following table. And in that table, what happens, it shows the publications by country in 1980 and 2021. There were no papers from China in the top 10 in 1980. But by 2021, it was the leading country producing fluidization papers. So if we look at this table, you can see in 1980 here, the United States had the largest percentage of papers of all the number of papers in fluidization. And if you add US and Canada, it was about 50%. Now you go to 2021, China now was the largest, had the largest percentage of publications at about 30%. It was roughly equal to the sum of US and Canada here. So in that period of time, China really took over the fluidization field, and the number of people working in the fluidization field even today is dominated by China. So this is just a plot that I put in here if people want to look at it. It's a history of the FCC process, where you say we started out here with the Houdry fixed beds here, the model, Exxon Model 1 and 2. You go through, you can see a lot of the things that were developed like UOP, riser cracking, et cetera. And you go through here. This is just a slide if you want to look at FCC and look at, say, the significant developments in the FCC field. I'd like to talk now about regimes in fluidization. There are different regimes, and the different regimes are dependent upon the velocity that you have in your fluidized bed. I've done this for a Group A material. What you have is firstly a packed bed where you don't have enough drag force to support all the particles and cause fluidization. And then for a Group A material, if you fluidize, and just barely above fluidization, you have this particulate regime where it's fluidized but you have no bubbles. Then you start to form bubbles into the bed, like this, a typical bubbling bed. And if you're in a research lab, what happens is if these bubbles get to be about half the size of the column, you have what is called slugging. You get severe fluctuations like this in the bed, and it's something you want to stay away from. Fortunately, in commercial systems, the units are so large you really don't have to worry about slugging. Maybe in pharmaceuticals where they have smaller diameter beds, perhaps, but with big beds, you will not get slugging because the bubbles don't get to be half the size, say, of a 50-foot diameter vessel, that sort of thing. So once you get to bubbling beds and you increase the gas velocity, you get into what's a turbulent bed. The turbulent beds really don't have any stable bubbles, but they have these voids that they can break very quickly, and so you get high rates of heat and mass transfer. And that's really where almost all FCC regenerators lie, in here, or they go into what is called the fast fluidization regime. This fast fluidization regime is now different. These are all dense fed. When you go to the fast fluidization regime, it's actually a pneumatic conveying type of system. So, and it's the densest part of the pneumatic conveying system here. And what you have when you look at dilute phase pneumatic conveying, you have delta P over L versus gas velocity here, and you get this U-shaped curve that you have here at one constant solid flow rate through the system. Well, the reason you have this U-shaped curve is because out here at very high gas velocity, the frictional forces dominate in this particular area. The frictional forces are gas to the wall, particle to wall, gas to solids differential, delta P, delta velocity. And so they dominate out here, but they will come down like this. The other term that you have is static head of solids. The static head of solids at high velocity is very low. Everything's are dilute. When you decrease the gas velocity, what happens is you start to increase the concentration of solids, and it increases right here. They're about equal, the frictional and the static head of solids terms. But here, between what we call a choking velocity, which separates the dilute phase from the dense phase, between this point and here, this is called the fast fluidization regime right here. And that's where the FCC risers operate. Okay? It's the densest part of the dilute phase pneumatic conveying regime. So for many years, people looked at these regimes here, and we really know what happens now. There was a huge argument in the 70s and 80s about where the fast fluidization regime was. Some people said it's here. Some people said it's here. Now we know basically it's right here. Okay. So fluidized beds have been spectacularly successful as devices to produce industrial products over the last 100 years, especially in the chemical and petrochemical industries. So the characteristic advantages of fluidized beds that make them such widely accepted and highly efficient devices are listed below. First of all, they have excellent heat and mass transfer. For heat transfer, it's an order of magnitude, 8 to 10 times what the heat transfer would be in a packed bed. So that's one thing. Also, you have precise temperature control. The rapid solids mixing in these beds results in nearly isothermal conditions with temperatures throughout the bed within 2 to 5 degrees C. And that's one of the best diagnostic tools that you have in your fluidized bed, is to look at the temperature distribution across the bed. If it exceeds more than 10 degrees C, you should start to worry about whether that bed is operating correctly or not. Okay? So it also has a small footprint. Due to the excellent gas solids contacting and mixing, fluid beds require smaller reactor volumes to achieve the same throughputs as other technologies. And then it has fuel and material flexibility. Fluid beds can accommodate a wide range of particle sizes and use combinations of different materials. And you can say for a chlorinator, where they have coke and titanium ore. The titanium ore is 150 microns, the coke is 1,000 microns, but you have to fluidize both at the same time, and they do it very successfully at also about 1,800 to 1,000 degrees C. So it's people are very creative, and they've been able to use this field to apply it to all sorts of different types of processing. So today the fluidization field is at a stage of knowledge development that is significantly greater than it was even 20 years ago. Okay? So now you have diagnostic techniques that have been developed that allow the determination of gas and solids mixing. You have mathematical models that are at a helpful stage of development now, and I'll say a little bit more about that. And the scale-up of fluidized beds is still an issue, taking time and money, but there's less variability in scaling up and more understanding of how to proceed with it now than there were 20 years ago. So the knowledge of fluidization regimes and how each regime should be used with each type of reaction and particle size now is pretty well understood. But what is not known definitively is how to predict interparticle forces and behavior of cohesive particles. That's extremely, extremely difficult. So this is an area that will be studied more extensively in the future. And probably if I were a young engineer going into this field, I would probably gravitate to that area because there's going to be a lot of work in this area. So today there are extensive techniques that have been developed and perfected over the years that can be used to evaluate what is occurring in the laboratory, and some can be applied to hot fluidized beds. So I'm going to list just a few of these things. First of all, they're optical probes, and they've been around for quite a while. These use optical fibers to transmit laser light into the bed and then detect backscatter. The probes can determine bubble properties and particle concentration in the bed. Then you have gas tracers, generally using helium, or maybe with CO2, some other gases, sulfur hexafluoride being one. Generally using helium with thermal conductivity detectors, and you can determine the degree of gas backmixing and the amount and direction of gas flow. Then you have fluorescent-coated solid tracer probes and solids. The motion and concentration of solids dyed with fluorescent coating can be determined with probes, so you can determine mixing and how fast the mixing occurs in the bed. And then you have electrical capacitance tomography. It's a non-invasive technique that determines the spatial distribution of solids in the bed. Then you have electrical capacitance tomography. It's also a non-invasive technique. And then there's a high-frequency differential pressure probes, which we use a lot at PSRI. And the fluidized bed behavior can be related to measuring the standard deviation of bed differential pressure drop fluctuations. Now, the normal frequency of a fluidized bed is somewhere between 2 to 5 hertz, so you need something, say, an order of magnitude greater than this, somewhere 25, say 50, or we say about 100 hertz, and you can look and see what happens in the bed, and this gives you a lot of information. Then you can have an extraction probe, a tube that is placed in the bed, a dilute phase line to measure the mass flux distribution across the line because it's a movable probe. And then positron emission particle tracking, which is called PEPT. It's it's really a very powerful tool, but it can't be used in large units. But it's a non-invasive technique where a single particle is labeled with a positron emitting isotope. It's inserted into an unlabeled bed of particles, and then detectors surrounding the bed monitor the position of the particle as a function of time. So you operate this thing over, several minutes or whatever. You can see where the particles have gone and that sort of thing, and see how it mixes and that sort of thing in the bed. Okay. So there are hundreds of fluidized bed processes that exist today. However, there are several that are deemed to be important either due to their size or the relative importance of the area. So I'm going to talk about some of these. It's certainly not an exhaustive or all-inclusive list, but FCC, okay? This process is still the oldest and most important application of beds today. This process converts crude oil into gasoline, diesel fuel, jet fuel, LPG, polypropylene, etc. Then there's a synthesis of polyethylene and polypropylene. So the fluidized bed for this particular process allows really effective heat removal and precise temperature control to prevent the melting of the resin. So they operate within about 5 degrees C, they have the melting point, something like that. Then there's fluidized bed combustion, the CFBC, where you have a circulating bed, burns, say coal, biomass, whatever, fuels in a suspended dilute phase mixture of ash and limestone for power generation. It captures sulfur and reduces NOx. Very large units. For instance, these big units that you'd have, a lot of them are in Poland and China. They're rectangular in nature, and they rectangular in nature, say the long length of the bed would be longer than the length of this room. The width would be, say, maybe, half to 2/3 the length of this room, and they're 200 feet tall. And they have cyclones that are 10 meters in diameter. That's bigger than some fluidized beds, but these cyclones work, right? And they'll have 4 of them in parallel sometimes. So these are huge units that you have, and it's amazing. They work with about 150 micron particles. Then you have polysilicon, and fluid beds are used for chlorination and thermal decomposition of silicon, and produce ultra-high silicon for semiconductors and solar panels. Okay. Then you have biomass and waste gasification. Fluid beds are used to convert, say, municipal solid waste and biomass to syngas. Roasting of sulfide ores, where you take copper, gold, and zinc sulfides. They're roasted to extract metal oxide, produce SO2, mainly for sulfuric acid production. And then drying. You have all sorts of fluidized beds, different types for different materials. They're used to rapidly and uniformly remove water from a wide variety of materials, especially in pharmaceuticals and food. Then you have granulation and coating. A liquid is sprayed onto a dilute phase suspension of particles which produces free-flowing granules, say food, pharmaceuticals, catalysts, fertilizer, etc. Okay. So these are some of these processes that I talked about. This is the UOP side-by-side FCC process. I'm just going to go get a few highlights. The thing is, these things are huge, and you move solids around here 80 tons a minute or so. Some are even more than that. But what happens is in these beds, you have a riser cracker right here where you deposit coal and it reduces the activity of the catalyst, and you take the catalyst and burn off the carbon, which reduces the activity, and you cyclically move this around here. What happens is that they have different sorts of fluidization regimes. This is the fast fluidized bed regime here in the riser. In the stripper, which you take to remove the gas products from the particles before you take them over here to the regenerator to burn off the coke, is in a bubbling fluidized beds with baffles. And then you have a regenerator here, which can be, generally it's either a turbulent or you can have fast fluidized beds as well. But almost never will this be a bubbling bed because it doesn't give you the heat and mass transfer that you need here. And the standpipes here. Basically, you want to operate them in a bubbling bed with as few bubbles as possible. That's one of the things you need to do with a standpipe. Okay. And then this is a polyethylene reactor. It's a very high pressure, low temperature reactor here. So what happens is it's a group B material and very large beds, 14 meter, 45 to 50 meters tall, that sort of thing here, maybe 5 meters, 16 feet in diameter. And this one has no cyclones. It's one of the processes that doesn't have cyclones. They take the fines, and they've learned how to break these fines, to reduce them here with an expanded freeboard, but then take them through a compressor and a heat exchanger before you go back into the bed. So you bring in a catalyst, and then on each catalyst, then you basically, like an onion skin, grow polyethylene and this sort of thing. Now, this is one of these circulating fluidized bed combustors that I talked about being so large here. It's a rectangular device where you put in air here and you have the circulating bed. This operates in dilute phase. You go into this very large diameter cyclone that I talked about. Almost all of them has something called a loop seal to take the solids right back into the bed. So the unconverted coal and ash will come back here and you'll circulate everything around. And then this is a very simple ore roasting type of bed. It's a very strongly exothermic device. You bring in your ore feed here. You have tubes in the bed to cool everything out, and you have an overflow here. So it's a very simple type of bed. Okay. And here's selected fluidization applications through the years. So you can look at this slide and see basically where everything started. For instance, the Houdry catalytic cracking in a moving bed occurred right here. There's the Exxon FCC concept. You had fluidized bed dryers, etc. So you can see over the years where these fluidized beds were developed and where they came into prominence. Okay, now I'd like to talk a little bit about the future direction. So I go back to this famous philosopher and baseball player, Yogi Berra, right? And some of you know who he is. He said, it's tough to make predictions, especially about the future. So even though it's difficult, I'm going to try to make some predictions here regarding some of the fluidized bed processes that could be more prominent in the future in the direction of some fluidization research. Okay, so today, the fossil fuel processes that have been the backbone of the fluidization field are slowly declining in importance, right? Everybody wants green technology. So they go to sustainable and green technologies, but some processes that are expected to become more prominent are listed below. First of all, there's calcium looping, which is a type of chemical looping. And this is a regenerative, cyclic, high-temperature process that uses inexpensive limestone to capture CO2 from fuel gases in the stack, right out of a process or a company. So it produces a nearly pure stream of CO2, which then you can use, or you can use it industrially for enhanced oil recovery or whatever you want, or you can store it, whatever you would like to do, okay? Then there's methane pyrolysis. We're getting a lot of, the last several years, people have come to PSRI and talked to us about different variations on the theme of methane pyrolysis. Mainly it means how to heat the bed differently. It's also called methane cracking, and methane is broken down into a clean hydrogen plus a valuable carbon product. So this process does not release CO2 and is a highly efficient method of producing hydrogen as well. And some people actually want to produce the carbon because it's more valuable than the hydrogen. Then there's plastic pyrolysis. This process heats plastics in a high-temperature fluidized bed. It breaks down long polymer chains into shorter hydrocarbon molecules and produces oil, gases, and char. Okay. So this is one of the circulating fluidized bed calcium looping system, where you take the flue gas right from the stack, you'd go through what is called a carbonator right here, and then this would basically be a CO2-free gas that would come out of here. So you take the solids from here and take them over to here, for instance. This might be, and then this would be called the calciner. In this particular reactor, you might have CaO plus CO goes to CaCO3. You take the calcium carbonate here, and then the plus Ca goes basically to CaO plus CO2, and you get an enhanced CO2 stream here that you have. Okay. Now, in the near future, more experimental work is going to be directed towards cohesive solids, materials smaller than 30 microns on average size. They're very difficult to fluidize and transport, but because of the high surface area per unit volume, people want to use these materials. So they're very difficult to fluidize and transport. And they're very, very difficult to do that. So PSRI has already seen much more interest in these materials in the last few years. We've developed new techniques and equipment to allow fluidization of these materials. So we've made a great inroad in how to handle these and to fluidize them and that sort of thing. But still, we need to go much further. So the interparticle forces which cause cohesion can cause small individual particles to agglomerate together instead of behaving like individual particles. So these interparticle forces are van der Waals forces, electrostatic forces, capillary forces, etc. And these forces can also cause material larger than group C, say group A material. If you put some group A material into your freeboard, some of this group A material can agglomerate as well. So it's not just group C material that you have to worry about agglomeration and clumping. So this is apparent in risers as well as in the freeboard of some group A particle beds. However, the interparticle forces which cause cohesion are different with each particle. I think we had a zinc material. We found it extremely difficult to fluidize, where some other group C materials were relatively easy. So we don't know why this is, and how to predict these interparticle forces, but they're definitely different for each material. So it's expected there's going to be a large increase in work in this area in the coming years. Okay. So this is a slide that just shows you what can happen. So basically, you really can't consider a riser, at least with group A material, as individual particles going through the riser. Because what happens, you're going to have these assemblages of particles that look like this going up the riser. And even in a fluidized bed, if you're in trained material from the bed, will not have individual particles if you're group A. Maybe group B and group D, yes. But for group A materials, you're going to get this same thing happening here. And there are many papers on this. So this is a fluid bed with agglomerated particles in the freeboard. Okay. Now this is supposed to start automatically, but I want to show you some of what happens with group C material and why it's so difficult to work with. So we just added gas to this bed of material. It's a semicircular column here. Then it breaks up and it starts to fluidize, but then what happens, it goes through what is called a rat hole. So the gas goes through this rat hole that it has here instead of fluidizing. It'll maybe revert to a fluidization for a few seconds, and then it'll revert back to rat holing where the gas just bypasses the bed. This is obviously not something that you want to happen if you're trying to fluidize this material, but there are ways to actually make this material fluidize better, okay? And let's see, I should try to do this. Okay, so this is some information on FCC catalyst, and this is low solid flux, high solid flux, low velocity, high velocity. So this is actually where FCC riser operation occurs, and you can see the solids are going up along the wall. A lot of people think that they reflux back down, but they do not. But you can see here that in some of these cases, you have these individual elements here. They're not individual particles at all, but you have streamers, agglomerates, clumps, and that sort of thing. So this makes it very difficult, and also makes it very difficult to, for modelers to predict extremely well. So everything is becoming more complex, but people are very creative, and they're learning how to handle these sort of things. So it's also been readily apparent to people working in the fluidization field that the number of papers on mathematical modeling has increased tremendously over the past 35 years. Because of this increase in modeling, PSRI issued what we called 3 challenge problems to modelers, and what we wanted to do was obtain a sense of how accurate the models were and if the models were improving. So data was produced in the PSRI test units, and this information was given to the modelers, not the results, but the size of the units, the velocity, et cetera, the solids flow rates. And we said, we'd like to have you model, say, the mass flux distribution across the riser, see if you can predict that, okay? So the modelers were asked to predict these values. Then the first PSRI challenge problem results were shown in 1995, and the second challenge problem results were published in 2001, and the third was in 2011. So it's about time for another one, I think. So in challenge problem 1 in 1995, the modelers were asked to predict the measured radial distribution of solids mass flux in an 8-inch, 20-centimeter diameter riser as a function of gas velocity and overall solids flux. And the conclusion of the exercise, people, was that the models were not sophisticated enough to be used to predict the hydrodynamics in a CFB. Okay. So in challenge problem 2 in 2001, the modelers were asked to predict, again, the measured radial distribution of solids mass flux in the same 8-inch or 20-centimeter diameter riser as a function of gas velocity and overall solids flux. And the conclusion of this exercise was that even though there was a demonstrated improvement, that the model still needs substantial development to be able to predict CFB hydrodynamics. Now, the last one was the challenge problem in 2011 was slightly different. Modelers were asked to predict the radial distribution of solids in a 12-inch, 0.3-meter diameter riser from NETL, and, which is the National Laboratory Riser, and also predict the density profiles in a 3-foot diameter bubbling fluidized bed at PSRI using FCC catalyst operating at different gas velocities and with different fines levels. Okay? In some cases, we knew that the bed was operating with something called gas bypassing, and I'll talk to you about that in just a little bit. So definite improvement was noticed in the models in this last challenge. There was a big improvement. However, the inclusion of gas bypassing case in the operation of the bed was a very difficult condition to model, and the models failed to predict gas bypassing, in my opinion. And the difficulty in predicting this condition can be appreciated on the next slide, and I'll show you what gas bypassing looks like. So although the models have been steadily improving, and they've improved since from 2011 till now, we've seen massive improvement. But there are areas where they are still lacking hydrodynamically, as in, say, predicting gas bypassing. So this is, I hope everybody can see this. This is a fluidized bed of FCC catalyst that is a 4-foot deep bed right here. And you can see everything is fluidized extremely well. So when we go up to an 8-foot deep bed, however, now you see gas bypassing up here, just like a stream of gas here. And we go to a 12-foot bed, it's even more prominent. You can see the gas bypassing here. So you don't get good fluidization here if you get into these conditions where you have a deep enough bed or whatever conditions that gives you gas bypassing. And that's extremely difficult to model. I think it's kind of extremely difficult to model. So the other thing is that's important at PSRI, which has been the success of modeling, is that we have what is called a jet cup, and we use this jet cup to measure particle attrition. So what we had was a cylindrical jet cup that looked like this, and from the top view, what happens is we have a tangential inlet tube that comes in here. So we fill this up with about 100 grams of material. We operate for a period of time. We look at the particle size distribution that we put in, and then what happened afterwards, and we can see how the fines concentration increases or the particle size distribution changes. Okay, so we were using this, and we got some material from an attrition in a fluidized bed here. And we wanted to use the jet cup to predict what was happening in here because it's much easier to operate the jet cup than this big fluidized bed. And so what happened, we used this jet cup, and the data were all over the place. And so what's going on here? So we started to model. We used the CPFD code and applied it to this jet cup. We tried to figure out what was happening in the jet cup. Well, when we used the code said, well, one of the problems that you have is that you have a stagnant material here in a stagnant region in this particular jet cup, and that's one of the reasons why you're not getting the data that you wanted. So we called them back and we said, oh, it said your code isn't working. It says we have a stagnant material in the jet cup. Well, okay, so what we did was we looked at this. I'll see if I have it here. Yeah. Okay, so this is what the code predicted, that you would have a stagnant material here in the jet cup. So he said, well, we'll just make a plexiglass column, and then we'll look at it and see if it occurs or not. Lo and behold, we had stagnant material in here. So the CPFD software code correctly predicted exactly what was happening in the system, that we did have stagnant material. So the way we solved that problem was to use a conical jet cup like this. When we have a conical jet cup, then basically 99% of the material is in motion when we do our tests. So that was it was a big success, and it really helped us out a lot when we used the modeling there, okay? So I'm going to go to the next slide. It just shows the more dimensions of this conical jet cup that we developed. But it was basically because of the modeling CPFD software, which allowed us to get into a device which was successful, okay, in using in predicting attrition. So there are two areas where modeling can really make a difference in the fluidization area in the future. This is my opinion. One area is in decreasing the time to scale up processes and then troubleshooting of existing processes using especially Geldart A, the larger group B and D particles. Scale-up assistance and troubleshooting with models are being utilized now, but demonstrating improvement in the accuracy of the models would engender much more confidence in using them. For instance, it might help if the models could predict gas bypassing. It would also help if they could predict what is happening in the Group A standpipes, which is a very difficult thing to do. Okay? Lauren talked about that in the last couple of days. So even now, when not fully developed, however, modeling is a valuable tool to use in assisting in scale-up and troubleshooting. CPFD software has been remarkably successful in modeling large fluidized beds such as FCC regenerators and predicting results which are helpful to operators, like if you would change some of the equipment that you have in the bed, how would that affect the operation of the bed? So although it is a very useful tool, most people do not have the confidence to solely use CFD models for scaling up a process. This may never occur, at least in the near future. The traditional experimental route of pilot and demonstration plants takes a lot of time and is costly, but it is proven and it will take significant advances in modeling to replace this approach with modeling alone. You have to get the confidence to use it. But it would be wonderful, wonderful if that, and you're making inroads on it. So the capability of models will continue to improve as computers, or GPUs, become faster and model development continues. Fluidized beds contain trillions of particles, perhaps even a quadrillion, which is 10 to the 15 particles. And the capability to apply models to individual particles, to determine particle-to-particle interactions and determine if they will form agglomerates, et cetera, appears to be a significant distance in the future. So with CFD and DEM coupling, perhaps as many as 10 to the 7th or 10 to the 8th particles can be used today. Now, I like the way CPFD software does it with the multiple particle in cell approach, because then you can estimate and you can get some realistic things to apply to these fluidized beds. So, but for modeling to achieve this ability to take on a greater role and scale up, as well as to be able to predict the hydrodynamics in beds with different particle sizes, especially group A, and group C, I think, is, in the future, right? People want to go into group C. I only know of one process using group C today. Only one, okay? So there's not like there are 100 processes out there with group C that you have to start to model. But if you could do something there, I think there will be more in the future. But anyway, there's only one today. Normally in the fluidization area, improvements are evolutionary instead of revolutionary. So if this progression continues, it seems that a significant increase in processing power will have to occur to be able to apply hydrodynamic modeling to individual particles on the scale of industrial fluidized beds. So Peter and Sam and the rest of you may want to address that. Maybe I'm wrong. The other question I have is, can quantum computing be applied to CFD or CFD? I have no idea. But they're saying that there's a quantum leap in the capability of using models and that sort of thing, and being able to to process these sort of things. So thank you very much. I'll be glad to try to take some questions.
It's beautiful, Jed. We know you as the L valve person. What's the history of the L valve?
What is the what?
The history of the L valve.
Okay, I can tell you about the history of the L valve. I didn't invent the L valve. That was done by some other people who were before me, and when I went to coal gasification, they put an L valve into one of the gasifiers, and it didn't work. And they were, what's going on here? Why didn't it work? So I started to do some research on it. So basically, I was the one who explained how the L valve worked in a few papers, right, and that sort of thing. But I didn't invent it. But there's like everything, there are operating limits and that sort of thing, and so I sort of showed that that's the case. So that's the history of the L valve. It was known in about 1970. That's when people first started to use it, okay, up until now. Yeah. And there are two types of L valves, if everybody knows. There's a type that will control the solids flow rate. That will only work with group B and D materials. Then the other L valve is the automatic L valve, where you put it in, say, below a cyclone, and you automatically take solids, go through it. It'll work with any type of particles. So there are two types of L valves. You just have to design them correctly. Okay.
Any other questions? I had a question about one thing you mentioned was just the vast increase in publications coming out of China compared to some of the other countries. So have you seen any corresponding innovations that are like fundamental to fluidized beds accompanying those publications?
I wouldn't say they're something like a step change, but there have been incremental improvements. And the Chinese, for some reason, are able to do work on a large scale. They work on large scale, whereas people in the United States tend to be on medium to smaller scales. And so the data coming out of China, is on a large scale, and so you can trust it. And they're very creative about what they do, and they develop techniques and that sort of thing. So there's been a huge improvement in the fluidization field that has been done by the Chinese researchers. Yeah. But now, I would say, probably 50% maybe of all the papers in fluidization are due to people working in China. Something.
Interesting. Yeah. A question from Peter here.
So Ted, first of all, thank you for doing this and sharing the history. I've benefited from some dinner conversations where you've shared stories about fluidization that just are great. So let me put you on the spot here. Can you share either where you were very surprised by something in fluidization? I mean, you get the jet cup, but not necessarily related to modeling. Like something came up and you were either surprised by that, or a story where had the people at the time have the knowledge that we have today about fluidization, fluid particle processes, that something went really badly and it's obvious in hindsight.
Yeah. Actually, the thing that shocked me was the gas bypassing. I didn't realize that it was, and nobody else knew about it either. And some of the old timers with some of the old catalytic processes said their beds wouldn't operate very well. They didn't know what was going on, And once we came out with this concept of gas bypassing, they said, aha, that's what was happening, okay? So if people had known that a long time ago, things might have been a little bit different. But that shocked me that it was such a step change in the operation of the fluidized bed. Yeah.
Jim?
So when PSRI, or if PSRI does another challenge problem, should we expect to see gas bypassing be present in there?
Yes, definitely. If we do another challenge problem, we'll have some beds that have gas bypassing in there.
Maybe
But we won't tell you.
Right.
So you have to be able to predict it, okay? But yes, we'll definitely do that. Yeah. But I'm very impressed with the way the new models have improved over the last 10, 15 years. So I think a new challenge problem would show that as well. Yeah.
All right. Well, thank you, Ted. Let's
Okay.
give our speaker one more round of applause.